Seismic resistant building features. Earth's moving plate causes sudden energy release, which causes ground motion on the surface. Strong shaking can topple buildings and cause widespread damage. However, the seismic design makes buildings more earthquake resistant. Buildings flex, absorb, and redistribute shaking forces, reducing the collapse risk. Engineers began to systematically study the impact of earthquake on different structures. By analyzing the damage patterns, they identified the critical vulnerabilities and areas for improvement. Based on the observations and scientific studies, engineered solutions were developed to improve the seismic performance of structures during an earthquake. This involved incorporating features like expansion joints, base isolators, bracings, mass and liquid dampers, shear walls, and structures with proper corner connection for box action during earthquake. This model highlights a multi-layered approach to create earthquake-resistant structures. 1. Seismic joints. Seismic joints act as gaps that allow movement, reducing stress and preventing cracks or failure in critical structural elements. It also accommodates thermal expansion and contraction, ensuring the building functions properly. By isolating movement between building sections, seismic joints minimize the risk of cascading failures during earthquake. The selection of ceiling material depends on specific application. Common choices are 1. Polytetrafluoride TP, 2. Silicone, 3. Thermoplastic elastomers TPEs. The size and type of joints are crucial. Seismic joints allow larger movements than expansion joints. 2. Base isolators. Base isolators are a cutting-edge technology that decouples a structure from shaking ground. It consists of elastomeric bearings, which absorbs and dissipates the earthquake energy. Base isolators allow building to sway slightly in a controlled manner, minimizing damage from earthquake. Implementing base isolation requires specialized engineering expertise to ensure optimal performance. 3. Bracing. Bracing systems act as the building's internal skeleton, providing crucial stability during earthquake. Bracings are typically made of steel or RC, which acts like diagonal strut and transfers forces down to the foundation, maintaining building's structural integrity and prevent collapse. Specific type and placement of bracing depends on the building's size, shape, and expected seismic loads. 4. Tuned mass damper. A tuned mass damper consists of heavy weight suspended that is carefully tuned to resonate at the same frequency as the building's natural swaying motion. As the building starts to sway in one direction, the mass damper sways in opposite direction due to inertia, thus reducing the overall sway. The effectiveness of mass damper depends on proper tuning. Mistuned dampers can worsen the response during earthquake. 5. Shear walls. Shear walls act like solid barriers that are strategically placed throughout the building to transfer the forces down to foundation. It helps to maintain the structural integrity of building and prevent excessive swaying or collapsing of the building during earthquake. 6. Proper corner connection. Corners are naturally prone to stress concentration during earthquake due to convergence of walls. Walls meeting at corners should be well connected to ensure it act as a unified element box action. It should be designed following the established seismic design standards to meet the required strength and ductility criteria. 7. Liquid mass damper. The liquid mass damper consists of water tank filled with water that is carefully tuned to resonate the same frequency as the building's natural frequency during earthquake. When the building sways in one direction, the water sloshes in opposite direction, which dampens the building's movement and minimizes the sway.